These are some properties of infinite limits. They're very similar to properties of regular limits, but there are a few small differences. So let's let c and L be real numbers and let f and g be functions such that the limit as x approaches c of f of x is infinity, and the limit as x approaches c of g of x is a finite number L. So the first one is the sum or difference. So this says that f of x plus or minus g of x is going to be positive infinity. The limit as x approaches c of that. Let's think about why that would be. You've got f of x, which is approaching a really large number. You've got g of x, which is approaching a finite number. Now f of x is growing without bound. It's increasing without bound. So if you take a finite number and either add or subtract that number, it's not really going to change the fact that it's increasing without bound. So that's still just going to go to infinity. Now, if you had your f of x as negative infinity, it would be the same thing. The answer would be negative infinity. So it just kind of depends on whichever one it is. Now, the product depends heavily on the sign of L. So if we let the limit as x approaches c of f of x times g of x, remember f of x is growing without bounds, g of x is a positive number, L in this case, so L is greater than 0, then that's going to approach positive infinity. And if the limit is x approaches c of f of x times g of x, where L is less than 0, that's going to approach negative infinity. So that negative constant L is going to turn that increasing without bounds into a decreasing without bounds. If your function f happened to approach negative infinity, you could reverse those two. So the constants do change the direction of the increasing or decreasing in some cases. Now, the quotient is interesting. So the quotient is the limit as x approaches c of g of x divided by f of x equals, and this one is equal to 0. So let's think about why that would be the case. You've got a constant number k divided by, and we'll put it over here, a constant number k divided by something that's growing without bounds. So you've got a fraction where your denominator is growing and your numerator is staying constant. So what happens to a fraction when your denominator gets bigger? Well, it approaches 0. One thing that you'll see that's very similar, kind of another flip side of this, is that if you have a constant k and you have a denominator that's approaching 0, this is actually going to approach infinity. And we'll talk about what those look like in some cases as well. So those are just some shortcuts that you can remember. If you've got a constant k divided by something that's approaching infinity, your limit's going to be 0. And if you've got a constant k that's approaching, or with a denominator that's approaching 0, that's going to approach plus or minus infinity, depending on how your signs work out. So I'm going to look at this same limit with two different approaches. One of them we're going to use the properties that we just saw, theorem 1.15, and the other one we're just going to go kind of the old school approach and just plug in numbers and graph it and see what it looks like. So what I could do from the theorem, number 1, the sum or difference, I could make this the limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. Okay, and this is just a constant, so this one is going to approach 1. Now in this case, I've got an example of the shortcut that I was talking about here. I've got k is 1, divided by something that's going to be approaching 0, because as x approaches 0, x squared also approaches 0. So this whole fraction here is going to approach infinity. So I've got a limit approaching 1 plus a limit approaching infinity, and if I add 1 to infinity, I still have infinity. So that's one way that you could do it. If you're not comfortable with that, you can always plug in. So I could make a chart. We're approaching 0, so I would get some points on either side of 0. We know that it does not exist at 0, and I can fill in the chart accordingly. So you can clearly see from that chart that as we approach 0 from either side, this thing is definitely approaching positive infinity, so that's one way that you can look at it. Or if you want, you can always look at the graph. And the graph looks approximately like this. It's a little bit more of a challenging graph to get than some of the ones that we've talked about, but we'll have some better methods for that in Chapter 3. So those are all valid ways to approach finding this limit. Okay, so if we're looking at this problem, we've got the limit as x approaches 0 from the right of 2 divided by sine of x. So we've got a number on top and we've got a denominator. So let's take a look at sine of x and what that would look like. So we know that sine of x, as we're approaching 0 from the right, is gonna have a very specific behavior. So sine of x looks like the following. Just a rough sketch of what sine of x looks like. So as x approaches 0 from the right, sine of x is going to also approach 0. So this is again a k, a number, over something that's approaching 0. And we said earlier the shortcut for that is anytime you have a number k over something that's approaching 0, you do want to look at whether it's coming from the positive or negative side. In this case, that's the positive side, and 2 is positive. This is going to approach a positive infinity. So the answer here is positive infinity. You could get that from a chart as well if you're more comfortable with a chart. Or you could look at something like this. This is actually the graph of 2 over sine of x. If you're more comfortable finding a graph, you can look at that as well, and you can see that as we approach 0 from the right, it does approach infinity. Now, another way that you could look at this is if you're really familiar with the graph of trig functions, you could turn that to 2 cosecant x and get your graph that way. Now let's take a look at this function here. We've got the limit as x approaches 7 from the right of x divided by 1 divided by x minus 7. Now most of you would probably look at this and say, why would you ever write this that way? And you're probably right, but sometimes these things come from applications or various other places, and so you do kind of need to know how to handle this sort of situation. So let's take a look at what's going on here. We've got the limit as x approaches 7 from the right of x divided by 1 divided by x minus 7. So there is a kind of an implied nesting here. Okay? So x, as x approaches 7 from the right, the numerator of this is going to approach 7. Limit as x approaches 7 from the right of x is equal to 7. However, this denominator, what's going to happen to it? Well, we've got a number, or a k, divided by something that's going to approach 0. So this limit is actually infinity, okay, judging by what we learned earlier in the earlier example. So the limit of this whole fraction here is actually approaching infinity. So we've got a constant number divided by something that's approaching infinity. So that is actually going to approach 0. And that will be your answer. And this all comes from the previous theorem.